Hi, today we are going to cover characteristic value and stress strain behavior of various materials. So, there will be 3 lectures which I am planning in this materials engineering concepts. Today is the first lecture, and these are the reference books which I use in this course module, and also we use a lot of information or photographs etc. from the internet. Now, outline of this lecture will first cover variability in various material properties, and then also how to address this variability in the properties in the design process. That is where we use something called characteristic value, and then also we will discuss about the stress strain behavior of various materials. We will cover elastic modulus, Poisson's ratio, yield strength, strain hardening, necking and failure, etc. So, variability and comparability of properties. So, I am going to cover just 2-3 material properties to tell you, where do we see the variability and what it is about. So, first let us say talk about density. What is density? It is mass of a material per unit volume of the material, and it can vary by significantly from material to material. From wood to metals, if you look at, there could be an order of magnitude difference of about 2. Another parameter is stiffness, which is ability of any material to resist deformation, and it can vary. If you talk about from nylon to diamond, it can vary in 3 orders of magnitude, and strength is another very important parameter which we look at while designing. Most of the time we give a lot of importance to the strength of the material, and it is nothing but maximum stress that the material can resist without failure. And from concrete to diamond, if you look at, there could be an order of magnitude of 4, like the difference in the order of magnitude. Now, toughness is another parameter where work, which is also known as work to fracture or fracture energy. What is it? It is ability to plastically deform and absorb energy until a failure occurs. Okay? And this, if you look at glass, the toughness is very low, whereas you will compare that to a very ductile material, it can be very high, the toughness can be very high, or in other words, the ductile materials can absorb a lot of energy before it actually fractures or fails. Now, this is a table with these properties we just discussed. For example, look at, I do not want to go through the entire table, which you can pause the video here and have a look at this table for a few minutes, and then you can understand the variability of these different parameters across different materials and also within the same material. For example, if you look at concrete, you can see that the density can vary from 1.8 to 2.5. If you are talking about stiffness of concrete, from 20 to 45 GPa. If you are talking about strength, again we are keep on modifying concrete. So, we see a lot of variability in the same type of materials by changing small things or the material design. So, in industry or when we practice, we see a lot of such variations in the properties of materials. Now, how do we use these properties in the structural design? We have to take care of the variability also while designing, and at the same time we need to be safe. Now, before we talk about that safety, I would also tell you, different materials which are used for similar purposes. Okay. So, for example, let us say you want to design a truss or a tension member in a truss. There you could use steel, you could use timber, many options are available. Okay. So, we for example, here you can see steel in a truss member and also wood. For both can take tension loads, tensile loads. So, what essentially we are trying to tell is that for a same application we can use multiple properties, multiple materials. Now, in such a case, how would you choose a material? Okay. For example, here also you have a brick column and a concrete column, a brick column and a concrete column. So, both will have different strength. So, based on the availability of the material, how costly each material is, and also we look at something technically which is weight of the material, what are the limiting dimensions and the minimum useful life or the durability part of it. Okay. So, cost is very important, and then you have to look at weight of the material and then limiting dimensions. For example, if you use a very low strength material for a column, you might have to have a very big column. Even in this picture you can see that brick column is very large in size, in diameter. If I replace that brick column with a concrete column with a very high quality concrete or high strength concrete, I can have a very slender concrete column. That will give me more floor space also. So, there are different aspects which we have to think about. If you are talking about a beam, if you use a wooden beam and in place of, if you are replacing that with a concrete beam, you can get more floor height. I mean, the clear distance from the floor to the bottom of the beam could be different in both cases. So, depends on various limiting dimensions which architects are always concerned about. So, we want to create more space inside our buildings, etc. So, these are different things which we have to consider. Aesthetics and personal preferences are also important to consider. Now, we talked about the weight criterion, right. So, how do we choose a material based on its weight? So, here I am going to show you an example. I am not going to go in detail about this slide, that you can view later or pause and understand these equations. But the example here we are talking about is a cantilever beam, where you apply a force F at the end of the beam or the free end of the cantilever. The thick black curve is the beam here, cantilever beam. And then, so you have an equation which tells you what is the deflection at free end, which is this u, and that can be expressed like this in this orange box. The equation u is equal to the load and then S cube divided by 3EI, where S is the length of the cantilever beam. Now, E is the modulus of elasticity, I is the moment of inertia. By looking at the cross section we can calculate that. So, how for a rectangular section, the I is defined as BD cube by 12, and now you plug in this I into the first equation or the equation in the orange box, you get like this. Okay, D is equal to 4S cube by EBU the whole to the power 1 by 3, and from that we can get an expression for weight, that is this here, and which is also d rho is the density. So, you can simplify that into this box here, orange box, where it is an expression for W. Now, W is the weight. Now, you look at that expression and look at different variables in that. Now, we know that this part here, okay, that part here is only dependent on the type of material which we use, the density and the modulus of elasticity. Both of them are material parameters. They do not change as the dimension of the beam is changing, but all other parameters can change. If you can change the load, you can change the length of the beam, width of the beam, etc. can be changed. But if you want to design the beam based on the material parameter and reduce the weight, you can say that this density, if I am going to reduce the density, it can reduce the weight. So, rho by e to the cube root of E is the parameter which you have to minimize, so that the weight can get reduced. So, if this is a product, right, this whole thing in the bracket is a product of the remaining. So, if I can reduce the value of this term inside the bracket, then I can reduce the weight. That is the idea. So, weight can be minimized by minimizing rho by E square cube root of E, which is a material parameter and which becomes the selection criteria for stiffness at minimum weight. Now, we also use strength as a criterion for designing material systems. For the same cantilever beam example, let me show you how that can be done. So, you can see here the same same diagram with the force F acting and the length of the beam as S. So, for this the maximum tensile strength can be expressed like this: sigma max is equal to 6 Fs by Bd square, and then we can express the weight using the second equation here, that is the weight. Now, here you have to see how, if I want to reduce the weight and also consider the strength as a criterion. So, I have to actually maximize this. Okay. So, for strength at minimum weight, the term this you have to look at the other way, rho divided by sigma limit. So, this is how it is, I just wrote it the other way. So, this has to be minimized. Okay. Now, if we need to minimize the cost instead of weight, okay, that is the third criterion. The selection criteria for maximum stiffness and strength are this based on the stiffness criteria and this sigma max criteria respectively, where Vc is the cost. So, you have to see whether you want to look at the weight or strength or cost, what is your main criteria, and then accordingly you come up with a formulation which will help you to minimize or maximize a particular parameter, and this is generally adopted in various applications. And then because it is not only strength and weight which you have to consider, money is also very important. So, that is why we also talked about cost. So, you have to think about various aspects and then see which is the most feasible solution for you to adopt. Now, so this is a table, you can look at this table here different. So, for you can see here for a diamond, for a same application, and I can choose different material, but the cost is going to be exorbitantly high in case of diamond. So, we may not go for it. So, but definitely you people sometimes compare, if we want, let us say for a building, if you are talking about column beam sections, whether a structural steel or concrete, which is better option for you to go. So, there cost can play a role. So, for example, here cost in case of steel, if it is 1, in case of concrete you can actually have read, that is the main reason why concrete is sometimes more popular than steel. So, different options are available, you have to have tables or information like this before you can choose what material to be used. So, when cost is neglected, sometimes diamond can be used, titanium, aluminum, wood, epoxy are the best, but when cost is neglected, but that is not the case in most applications. So, when cost has to be minimized, conventional materials such as wood, concrete, steel, they might be more beneficial. And of course, you have to think of that the time and location where you construct. For example, if you are talking about wood where a lot of timber is available, it might be cheaper there, but not in places where it is not easily or abundantly available. And also concrete, steel, all this depends on where the manufacturing plants are located, where the cement plants are located, and there are various factors which govern the cost of different materials. So, we have to think about the cost also while selecting materials in addition to the technical features. So, many important aspects are this table is very simple table. You have to also think about durability, toughness, construction time, transportation, etc., many other parameters before we really choose a particular material for construction. Now, there are mean and variability in the material strength. For example, you look at steel here, there is a term T here, that is standing for tension. All these T's in these are for tension, okay, and then C is for compression, like C here, that is for compression. Okay. Now, if you look at steel, let us say steel with a mean strength of 460 megapascal, and you can expect that the coefficient of variation of steel is about 2%. Variation of the tensile strength of steel is about 2%, and whereas the similar variation, coefficient of variation for compressive strength of concrete can be about 15%. Why? Because steel is a more homogeneous material as compared to concrete, and steel is manufactured with much better quality processes in the manufacturing plant, whereas concrete you use natural materials like aggregate, even cement. Cement is processed, we can say, but there are aggregates which has a lot of variability in their properties, and the interface between the cement and aggregate will also be different at different points within the concrete. That also depends on how the concrete was placed, how it was compacted, lot of factors play. So, we generally expect a wider variation in the properties of concrete as compared to that of steel. Now, in terms of in case of timber, we expect much more. You can see here 35, 18, 10. So, this is because you have you can look at here also different type of timber we are talking. So, if it is ungraded, that means more naturally available timber, you can expect much more variation in the properties. So, like in the fiber cement composite, you have less because it is more or less manufactured and also more better controlled, where even if there are cracks, etc., the fibers tend to bridge those cracks and minimize the variation in the properties. So, masonry also similar case. So, you can see these variability across different materials which are used, and that has to be considered in the design process. So, we cannot always use the mean value for design process. That means 50%, if I am using mean value for design process, it means 50% of the values are going to be above the design value and 50% is going to be less. So, that means there is very high chance of failure of the structure. So, what do we use? We use something called characteristic value. Okay. Now, what is this characteristic value? So, it is a variability of the strength depends on the uniformity of the structure and composition. So, lot of variability is possible. So, this typically we express this variability in terms of normal distribution in general, and then we use this word characteristic value. What is characteristic value? In the design and material selection, characteristic value is the value which we can consider as a safe value that corresponds to a value at which the probability of failure is at an acceptable level. Okay. It means, look at the graph on the bottom left. So, if I plot, let us say I do 100 tests on concrete cube, let us say I take concrete cube and take the strength, perform the strength test on all those cubes, and then I plot these 100 values, then I would get something like this. The number of results will follow something like this. This is what we call normal distribution. Okay. Now, so this is the strength of cube, it is plotted like this, and then for each value how many specimens actually have that particular strength. So, on the horizontal axis or abscissa you have compressive strength, and on the vertical axis you have number of values, number of specimens which gave that particular strength. Okay. Now, what I am showing here is the average strength of all those 100 specimens might be sigma m, which is somewhat, that means showing on the left side of this vertical dashed line you have 50% of the specimen, on the right side you have 50% of the specimen. So, here you have 50%, here you have 50%. That is the mean value. Now, if I use that value for design, what it means is that my structure will have 50%, that material will fail, the probability of failure for that material is 50%, because most other cases you will have 50% of the material might have a higher strength than the mean value, and 50% of the material might have a lower strength than the mean value. So, this is not something which is acceptable for design purpose. So, we use something called characteristic strength or characteristic value, which is typically assumed to be around 5%. Okay. So, this region which is shaded is typically taken as 5%. So that means if my average value sigma m, let us say it is equal to 30 MPa, okay, for the design purpose I might consider the characteristic value which might be, let us say 20 or 25 or something like that, okay, approximately 20 or 25, depends on the variability of the material. Okay. In case of steel, this difference between sigma m and characteristic strength will be very less. In case of concrete, it could be higher. Okay. So, you have to think about characteristic value, and that is the value which we use for design purpose and not the mean value, not the average strength. Okay. So, it is very important to consider. Now, let us look at some mechanical properties of the materials and response of the material to external loads. So, what are how these responses, they are dependent on the magnitude of the loads definitely, and the type of load. So, for example, type of load, if you look at, I am showing 3 graphs here: periodic dynamic, random dynamic and transient dynamic load. So, first one you can say periodic dynamic load. If you are talking about a railway track, or when a train goes through a particular point, you can say that every wheel it will come in kind of a very uniform way. The loading will be kind of uniform but dynamic, not uniform, periodic but dynamic in nature. Okay. Every wheel, when it passes, you will have, let us say the wheel passes here and then wheel moves away from that point, and then so load comes down, and again the following wheel comes and then it reaches, something like that. Okay. Now, if you are talking about random dynamic load, earthquake and wind loads are examples for that, and transient dynamic load, impulse or impact load. Let us say you have a heavy vehicle passing through a bridge. So, when the moment the vehicle enters the bridge, that column might experience an impact load, just a fraction of a second. So, you have that impact load here, and then it dies down as the vehicle moves away from that particular column. So, like this, different types of loads are there, and then definitely material properties influence the performance of the material, or how the material respond to the load, and also the geometry. Okay. So, these are material properties, and the size and shape of the elements also matter a lot when we think about the response of the material. Now, how the typical systems can fail? Okay. There are 2 types of failure. One is strength failure, the other one is serviceability or functionality failure. Okay. So, strength criteria is typically when we talk about something is collapse or fails or breaks into 2, etc. Okay. If we are talking about a strength criteria for a column, I can say that applied load is more than the capacity of the or the strength of the concrete material. So, that is a strength criteria. Whereas, if I am talking about serviceability, maybe it is something like deflection. If you are talking about a bridge, I can say the deflection at mid span or the center of the bridge has to be within let us say 1 centimeter or something like that, 1 centimeter or 2 something, some limit you will provide for the deflection. It is not that bridge is going to fall or break into 2, but there will be some deflection, but you want to limit that deflection so that it is comfortable to use that structure. So, that is one example of a serviceability criteria or functional criteria.